Next up is Dr. Rick Chalaturnyk from the University of Alberta.
Okay, so thank you very much. Thanks for the invitation to the annual summit. It's nice to be here in Brazil again. It's been a long time since I've been back. So I might change things up a little bit today. It's going to be a little bit of a different tone. Just to introduce the program, we're just about to launch, or have launched, a new one called Geosafety, about subsurface assurance. It's a number of themes, but in fact is governed by a couple philosophies. One is how little data does it take to be right in terms of the subsurface? And the other thing is, what does failure look like? And I'll explain that a little bit more even in the presentation today. But there is a poster downstairs that defines geosafety, and there are a couple things in here that I think we're very much looking forward to tackling. One is we've had a project now in Canada called Aquastore. It's been 10 years of dynamic injection under very, very crazy conditions, salt precipitation, all that kind of stuff. But we've really not actually got at the value of the data very well, and so we're going to use this march forward in time process to try and figure out when you're injecting subsurface information, when does it buy down the uncertainty to the point that you actually feel comfortable in your forward predictions. So we will pretend like we're standing in 2010, and then we will start with modern workflows and sort of work our way all the way through the dynamic simulations, testing it against 4D seismic, to try and find out that question about when, how little data do we need to actually be right. The other thing that I think that is really exciting is SIX, because I think these days now there's a lot of conversations about retrieval augmentation techniques, RAG techniques, to develop domain-specific LLMs and treat them in your projects. And so we're going to use this as an example as we march forward in time to test just how rigorous can we be in building what we call Aquastore GPT. Basically, there's a number of us that have been involved in this project for 10 years, and we have absolutely no idea where the data is. It takes us weeks to try and remember what happened in 2013. So there's some exciting stuff, and if you want to chat about it more, I'm happy to chat. But today, maybe a little bit of a comedy part of it. Leonardo introduced this a little bit, used the word stress path. Geomechanical engineers, we like stress path. Oh, it's compression, it's whatever. And the question is, it says, well, okay, but in some ways we're all being asked as reservoir geomechanics people to do these simulations in all of the scenarios around energy transition, but not just energy transition. I mean, conventional stuff. I would argue, although the pre-salt, pre-stiff rocks, but in other locations where rocks are going to move, those stress paths that you follow, if you're not treating them right way, we'll see if the end of the story is, if you agree with me, that we're actually leading the reservoir engineers down the wrong path. So let's see what it is. So obviously that's a very young reservoir engineer, by the way, but he's clearly stressed out. So let me tell you, so why worry about stress path? So Leonardo did this. I don't, a lot of questions, just a lot of figures. So we do simulations. You saw some pictures. Other people do it. Lots of people in this room, experts and stuff. And we do some modeling, and we put in a grid and a thing. And we've got stress strain, and we do some simulations. And we get these changes in stress and strain given whatever we're doing, be elastic, linear elastic for that matter. And when we do that, these elements that we have in these models, Ricardo said that there is a laser pointer. Oh, look at that. So we have these models, whatever they might be, and you have all of these grid blocks, and you're doing whatever, production, injection, that's thermal, CO2, hydrogen, doesn't really matter. And there's a stress path that's followed. And so there's all of these paths as geomechanics engineers. Again, Leonardo presented it, everybody presented it. I think Giovanni even showed the pictures. We do some kind of a test, we get a failure envelope. And there's a path that's followed in the model between all these elements. The thing that's interesting is that this is a very classic picture. It was done for very large water floods, looking at directionality in water floods. And he realized that there was a connection in this. This is the stress path, right? So this is the shear stress, the deviator stress, and the effective confining stress along this axis. And in this space, you can do all the fancy geomechanics stuff you want to, but there's a relationship that is embodied in this thing that's related to permeability. how permeability changes inside that space. So what's missing from these plots? If you're a geomechanics engineer, I'll point at you, Francisco. Hey? I won't pick on you, right? So what's missing from these plots? No, pore pressure's there. Volumetric strain. Because volumetric strain for us, do a lot of stress strain stuff. Everybody does that. Shear strength, the thing, move a more circle shifts. Oh, pore pressure goes up, more circle shifts. The whole relationship for a lot of this stuff related to permeability is related to volumetric strain, how you treat that in your models. And so the trick is that in general, you have a porosity change associated with the volume change, and the volume change for a porosity change then leads to a permeability change. And there are people in here I know who are experts in this and are probably falling asleep already because they know that we classically have ways of dealing with this. But the trick is that for the most part, when we do testing and you ask a geomechanics person to do testing, the easiest thing for us to do is to do what's a triaxial compression test. We take the samples, we put them in the lab, it's easy to confine the samples, load them vertically, fail them, and I can make measurements during that triaxial compression test. That's the geomechanics part. And so what's tricky here is that in this particular stress path, I'll make a point in triaxial compression, is that as I go along this stress path, for this stress strain curve, you know, my little sample, the mean stress in the sample is going up. It's a typical way I would do the test. I'm loading it, the mean stress goes up, which then impacts the volumetric strain, which then impacts how porosity change, which impacts how permeability changes. So what does it kind of look like? What about a whole class of materials? Mudstones, sandy shales, medium sandstones. I'll show you a bunch of other data to try and make this point about how I think we have to change the way we're thinking about this. So here's triaxial compression stress paths, and here is how the stress strain in black looks like for all these kind of ranges of materials, and you can see how permeability, and I should be starting to get exacting, absolute permeability changes in these materials. And you notice something kind of interesting at the very beginning of these tests. Permeability goes down, it doesn't go up. And it goes down because the mean confining stress in the specimen during shear goes up. Okay, so that's the stress path thing. So, huge history in this, right? Yeah, you don't have to read this. I just threw this up here. Massive history in this, okay? All the way back to some guy, Zobak. I don't know, I think he hangs out at Stanford or something like that. I'm sure everybody in the room hopefully knows who Mark Zobak is. I'm being facetious, of course. But all the way back to 75, even earlier, 1950, 1955, everybody understood that if you put a core in a cell, put on confining stress, change the confining stress, permeability would change. Absolute permeability would change. Okay. But this thing says, well, okay, but that's one path. So if you were back in that era of how permeability changed, we all know that in simulators you can put in compressibility, pore volume compressibilities, change permeabilities. What's the stress path that's followed in this space? The stress path for the majority of those tests, although it's in this particular thing it's going to change here in a little bit, the majority of the stress path in these locations is along that axis. It's a mean stress change. I put in a core holder, put on the stuff, put on the loads, unloads, whatever. It's inside that bottom line. It's not anything sensitive to the stress path. So if there's this huge long history, why now in this energy transition conversation are we worried about this? I think because now we're thinking about things like CO2 storage, we're thinking about hydrogen and other stuff, the context for this problem changes, and it changes quite significantly. So we have now, I've had the benefit now of working in the ISO standards now. This ISO standard, 27914, is under what's called FDIS. It's under the final thing. It now includes a chapter on quantification and verification. It's the one that de facto is going to define the international standard for geological storage of CO2. even in Brazil. So if you go to the international credit markets, the voluntary markets, involuntary markets, and you're going to actually value particular storage credits, there is going to be a sense that you've followed this ISO standard. So what happens in this ISO standard? It has all the language everybody in the room is familiar with. You'll see this, integrated projects, site characterization, risk management wells, and so on. But it asks us to look at things like deformations, casing integrity, caprock integrity, surface heave, and induced seismicity, and others. But the challenge in this particular new portion related to quantification, you have to model to failure, because we need to understand leakage pathways. Not fault. I don't mean fault reactivation. I mean, you have to take this system, not just put your injection conditions under normal operating conditions, you have to actually push the model all the way to failure and look at what your failure modes look like. And that's where this conversation around pore pressure and permeability change along stress paths, I think, is important. So this is a picture. Johnny Rookwitz did a lot of work. I'll show you a bit of his work before. So we do this. We saw pictures, prediction, part of everything, with coupled and almost coupled and partially coupled. And so if we know this, why should that, he's growing up now, he's a grown up guy, why should that reservoir engineer be stressed out? Because now to model failure, I need to provide evidence. I need evidence of conformance. I need assurance of containment. I need no adverse effects from the port. And the one that's actually really important is this one. Is this issue about no significant adverse effects of CO2 injection on health, environment. And that means you have to understand pathways. You have to understand the magnitude of the leakage, mass leakage rate to surface through certain pathways in order to complete your risk assessment. You need to know not only likelihood, you need to know consequence. So this has been tried. We tried this in Weyburn. I've been involved in the CCS world for a long time. Tried this in Weyburn. Full integrated risk assessment from the geosphere to the biosphere, identifying the leakage pathways, assets of concern, everything else. Next to impossible. It was a very, very, very difficult thing to do. Forward, there we go. So even in new quantification protocols, I took this from BC, but we have it in Alberta as well, and quantification protocols, which I suspect somewhere in the Brazilian regulatory world also will exist about how you quantify it, that it's specifically stated that you need to model potential pathways. Okay, so a whole bunch of arguments around that. So if we need to follow the model, we have to model failure and have critical leakage paths. I'm going to suggest to you that we're doing permeability variations wrong, and the kind of models that we're actually generating results from are not quite right. And that includes me, not just anybody. And Benham, just a warning, I'm going to come back to your paper but this is a great statement, this thing. I love the statement out of Benham's paper, the absence of coupling between flow and geomechanics. And it's what I'm talking about. I'm just going to suggest that maybe perhaps we have to change the way we do it. So doing this, though, is very complicated. So Giovanni talked about a few things here in the stress paths, and Giovanni's kind of chatting about this work over in this side of the world. There's direct and indirect tensile testing process and stuff. But there is a multitude of these stress paths that exist in all of these modeling scenarios. So let me go back and explain a little bit why I'm thinking this way, and I'm going to go back a little bit. So we've been spending a bit of time trying to worry about this absolute permeability stuff. I told Giovanni I'd show the picture about being out on an outcrop with a chainsaw. This is actually McMurray Formation oil sands that doesn't have any bitumen in it. This is an outcrop where the bitumen never made it. But it's still the same diagenetic history of this thing, so you can cut some samples, very dense, undisturbed samples, and you can look at how permeability changes. And one of the things we found is the kind of things I think most people would be familiar with, right? I do triaxial compression. This is back then. Triaxial compression test. That's the stress strain curves. There's the volumetric strain. And when I look at the data that you looked at from before, the blue is porosity. So remember, with the volumetric strain, the porosity goes up, but the permeability for the first part of this whole test actually drops like crazy. So I'm using a triaxial compression path, but my permeability change is just reducing like crazy. very rarely do you see this used in a simulation. Very rarely. Maybe a lot of people in here do it. The other thing that starts to impact this on stress path is that the relative permeabilities change. The relative permeabilities shift. Endpoints shift. This is equally as true for CO2 as it is for this particular scenario, and so on. So those are important. All triaxial compression paths. There we go. Relative permeability shifts. What about heterogeneity in the samples? This IHS got small layers in it. All of this stuff, we did this. So this is triaxial compression again as a stress path. And if you look at this in terms of triaxial compression, if I switch this around, now this is the start of the argument, to triaxial unloading. I go to the left under injection. The permeability goes up, but triaxial compression, the permeability went down. So if you're under an injection stress path, the permeability will almost increase instantaneously as opposed to using a model that you got permeability change from a triaxial test, triaxial compression test. What about pore pressure injection? What if all I had was an initial anisotropic in situ stress state and I injected pore pressure? What happens? So this is a case where the samples were actually initially loaded to anisotropic stresses, and the path I'm going to follow is move to the left from this red dot. So not down on this historical line down here, but from up here, what do I get? Well, what I get is, if I'm isotropic, I get the blue. I go up. That's the normal pore volume compressibility that you have in all your simulators. I go up and I come back down. Not quite exactly that, but I get it. But if I'm under anisotropic in situ stresses, I get this. And that's quite substantial. I immediately get a substantially different volumetric behavior and a completely different pore pressure. Go to tighter material, much more familiar with the sandstones that we're injecting into for CO2 and maybe perhaps for underground hydrogen storage and so on. And you can actually have geomechanical impacts that will shift relative permeability curves. You get the standard response normally, but it will shift capillary pressure curves, and it all depends on what stress path you follow. And now if you're under shear, Giovanni showed much bigger pictures. This was some interesting stuff done with a CO2 project in Japan, and they tested a bunch of different materials and looked at how the shear, but you can look at what happens in this stress path, in this particular case, with the permeability change. Again, all sensitive to thing. So what about modeling? So this is a very classic study, a long time ago. It's at Texas Stage where a lot of those cartoons that Johnny Ruquist generated. Big model, people look to this, coupled reservoir geomechanical simulations, all of the horizons, single permeability values in the model. And what was the stress path? So single permeabilities and all the stress paths are to the left and unloading under injection, except they're single permeability values that never changed. So it suggests to you that the simulation results in here aren't quite in the right direction, and we're going to need to understand that. And so this is a little bit, I just took the excerpt from Benham's paper because it was fast. I couldn't think, this is a phenomenal paper. But there's a chunk in here where most people are trying to do this in terms of training and doing coupled flow geomechanical simulations. And in general, in all of these simulations, this whole issue around permeability variation with stress path and how fast pore pressure will migrate up into cap rocks that will actually govern how the failure occurs. So we have to be careful about this. We do the same. We have a lot of difficulty. We need to generate more data that's much more sensitive to this path. So I think impending regulations are going to demand that our reservoir geomechanical simulations are not just about operational conditions that go all the way to failure. And to do that, we need not only just the constitutive behavior of the materials, not just the stress-strain response, but we have to understand how that permeability changes under all of those various stress paths. The failure processes are complex, and the experimental data is not going to be easy. These aren't straightforward. And I would think that this evolution of pore pressure, even within the reservoir, if you're an induced seismicity person, I mean, now there's an indication that this generation of induced seismicity off 5 kilometers away will be impacted by plus minus 200-300 kPa. These are tiny margins, and if you don't have that right, you're going to be in trouble. So I think it's important to understand the stress paths, make sure that you're generating permeability relationships that are relevant to those stress paths, and then you'll get the relaxed reservoir engineer on the bottom right. And so thank you to student and researchers. I mean, Jessica is here today. Karen is working on the Amigo project for depleted fields. She has a poster downstairs. Jessica's been working on really tightly coupled verification problems for sequentially coupled problems. Energi Simulation has been a supporter for a very, very long time. NSERC, industry sponsors, and industry sponsors of the new geosafety program. So thank you very much.
Thank you, Dr. Chalaturnyk. Question from the floor?
Thank you, Rick. More about, it's about relative permeability to show a shift in the curve of relative permeability. What about residual saturation, because it impacts in the, the trapping mechanism related to residual trapping mechanism.
How do you mean the reservoir saturation?
Residual saturation.
Oh yeah.
Yes,
it shifts.
Do you have some? Yes. Do you have some feeling about this?
Yeah. In fact, I would say if you're in the CCS world, which I think many of the people in the room are, there was a very, very extensive study done looking at multiple variations in changes in relative permeability curves, sort of a million shapes in the things, and found that really the dominant factor for the behavior was the shift in the endpoints, not the CO2, not the shape of the rel perm curve or anything else like that. So.
And also in fractures, I think that.
Sure, yeah. But generally, I mean, if you have 50 million fractures in a reservoir, most people don't model 50 million fractures. So people are having to sort of make some decisions on upscaling, right? So that's a tricky business on its own, but yeah.
Upscaling could be a challenge.
Yeah, absolutely. Didn't ask anything, but I suspect an undercurrent in most of this conversation is an upscaling problem, yeah. Yeah.
Mike?
This is a little off the wall, but can anything you've been doing say anything about salt cavern collapse?
It's as applicable to salt cavern collapse as anything, because rarely do you find a pure salt cavern. So penetration of pore pressure into zones, insoluble zones, stuff like that, will govern a lot of that behavior. So understanding how those permeability changes vary as a function of stress path are important. And if you use the wrong stress path permeability relationship, then you're not quite sure where your modeling's ending up.
Question online here. When the geomechanics provides updated porosity and permeability, does the reservoir engineer update their model so a truly two-way coupled hydromechanical model is simulated under different scenarios?
I'm a fan of sequentially coupled. In the research world, for tightly held problems, fully coupled helps us understand a bit of the mechanisms, but at large scale, I'm a full believer in sequential coupled simulations. There's ways to do it, very powerful. It's been proven if you use the right approach, you can actually get convergence and not a propagation of error. So if you build those models into sequentially coupled, there is no reason why that full coupling routine can't feed that back to the reservoir simulation. There's no reason you can't do that anymore.
Okay. Anyways, as a geomechanics engineer myself too, now that we're all stressed out, let's find a solution.
Did we go into lunch? I haven't taken you past lunch, have I? I hope not.
Not yet, another 5 minutes.
Okay.
So, are the current geomechanics simulators, like Abacus, Flex 3D, whatever, can they handle, in addition to this, the stress strain curves, volumetric strain, depending on stress path, can they handle that at the moment? Mm-hmm. They can. Mm-hmm. Okay, so then the missing piece would be the absolute perm in relation to that geomechanical response, as well as the relative permeability that you've done a great job on.
Correct.
So are there tools that's available now, or are you missing gaps that needs to be done?
No, the reservoir engineers just need to tell the labs what they need to do.
Okay.
I mean, that's, so I'm saying that if you're a geomechanics person and you're doing core, getting very expensive, I mean, it's very difficult, right? So the issue is that for us, it's very easy to just go off and do a triaxial compression test because we're normally dominated by understanding the failure strength. We've got to get C prime, phi prime, more Coulomb failure, but I would suggest that in this world of reservoir geomechanical simulations, and this energy transition work of CO2, hydrogen, and others, where the questions that are being asked are pretty significant questions that you just need to ask for the right kind of tests to be done so that you can input them into the models the right way. That's pretty much the message, I guess.
Okay.
Yeah.
Thank you.
Yeah.
Anything else from the audience?
Rick, very nice presentation. I have a question regarding the upscaling methodology that you would suggest for this, because in Denmark we work with shelf rock, with chalk, and so on. So depleted reservoirs, we see different sort of pathway, as you mentioned. We see in some reservoirs like Harold East, where it's depleted. So then, in order to get the history match, we have to basically play with permeability when it passes the pore collapse. But in the lab, we often have problem to get this sort of permeability variations and so on. What's your recommendation? How we deal with the lab work and how we go from lab to the
Yeah, that's a monster, right? That is a difficult one. The only thing that we've ever found a bit of success in is using, if you like, the same sort of numerical upscaling process that the reservoir simulation people do. So, flow-based, local-based, or even global-based kind of upscaling with grid blocks, and you put in the heterogeneity, and you do a flow test under a certain amount of scenarios, and you then upscale the parameters in some fashion. I mean, there's experts in the room. So we have actually found that one of the best ways for us to do it is that you've generated a grid in the reservoir simulation model, and then sequentially you've done a grid in the geomechanical code. And this is now typically a much larger grid block. And so what we do is you take the geocellular model, embed the heterogeneity inside, and run a series of geomechanical tests to rebuild the compliance matrix for this much bigger model and extract orthotropic properties from it. And that's the only way that we've actually found any success. And that actually allows you, you can use standard tools, but by pulling out these fully orthotropic parameters and using that as in your model, you actually can capture better this sort of global upscaled response. That's the only thing we've been able to do. Oh, sorry.
First of all, this is really interesting stuff to me.
Oh, thank you.
Yeah, it maybe sounds surprising, but it is. So
he's from the University of Calgary. That's very, very kind words to say.
That's right. That's right. I should be shot as a traitor.
Yeah.
Yeah. So I'm known to have measured a few perms in my career and a few relative perms in my career.
Absolutely. Yeah.
And it's my understanding that when you guys do triaxial testing, you use cubic or
no, cylindrical.
Is it truly cylindrical?
Cylindrical,
Good.
yeah.
Okay, so we can compare cylindrical samples to cylindrical samples,
correct.
Right? Okay,
yep.
Good. That's all. Thanks.
Yes. Yeah.
Okay.
Yeah, it's kind of a misnomer, that word triaxial, right? We always say that for triaxial, but triaxial we cheat because because you've got all around pressures. We just say sigma 2 is equal to sigma 3. That's all. It's just but that's radial and axial. Yeah.
Yes.
Yeah.
Okay.
And sorry. Yeah.
Thank you for your talk.
Okay.